In this video, I want to discuss modeling issues in developing the fluid mesh and the structural mesh. So we're going to discuss requirements for the fluid mesh, requirements for the structural mesh, the issues of coupling those two meshes, and then I'm going to illustrate certain principles through some examples. In linear hydroelasticity, we use a separate numerical method for the fluid and for the structure. And this is really true for the most part in nonlinear hydroelasticity as well. For the structure, we almost always use the 3D finite element model for practical structures. Some applications admit a plate or a beam model, but those are relatively few. The biggest challenges in linear hydroelasticity is developing the structural model and then coupling the two models. The fluid model itself is relatively easy to generate. In nonlinear hydroelasticity, on the other hand, the situation is just the reverse, and really the biggest challenge is the fluid models and the coupling, of course. In terms of structural modeling, the fluid mesh requires accurate geometric description of the wetted surface, but the structural model does not. The fluid mesh is concerned about the velocities at the wetted surface and then the pressures generated from the fluid. For the structural mesh, we require a detailed structural model, but it doesn't necessarily have to capture terribly accurately the wetted surface, the geometry of the wetted surface. It does need to have an accurate representation of the structural behavior. Here we're focused primarily on displacements and then the pressures coming from the fluid model, and in particular an accurate application of those pressures onto the structural model. So coupling the meshes is important, and in general we need to transfer velocities to the fluid mesh and pressures back to the structural mesh. However, in linear hydroelasticity we solve a tightly coupled system, and in practice we really only need to transfer the modal velocities to the fluid mesh. However, nonlinear hydroelasticity typically one uses a loosely coupled strategy, and there we do need to also send back the pressures to the structural mesh. So in coupling the meshes, we have three cases. In case one, the wetted surface mesh is identical to the structural mesh. And that means that every fluid panel corresponds identically to a structural shell element. In case two, the wetted panel mesh is kinematically constrained one-to-one to the structural mesh. In case three, the wetted panel mesh is kinematically constrained but not one-to-one to the structural mesh. And that means we need to do some interpolation. And quite frankly, I try to avoid this situation. So let's look at case one, which is where the wetted surface meshes are identical. So some students and I published two benchmark problems in the Journal of Offshore Mechanics and Arctic Engineering. And the first one was this barge shown down here, a rectangular barge, and it was designed to be flexible so hydroelasticity is significant. It's really just a closed rectangular box, 100 meters long, 10 meters wide, and 2 meters deep, with a 1 meter draft and infinite water. The mesh itself just consists of 6 flat plates, the top deck, bottom hull, the two sides, and the stern and bow plates. So material section properties that we needed, these were chosen to provide sufficient flexibility so the hydroelastic response is important. So modulus of elasticity was chosen to be 15 gigapascals. The thickness for the plates was chosen to be 0.05 meters. And we used the possibility of specifying a different thickness for the bending behavior of the plates. And remember, I mentioned this in our discussion about finite element modeling of the structures. And so this made it much simpler to generate the model because we didn't have to worry about internal stiffeners, which would typically be required to prevent local modes from happening. The mass distribution was set up so that to give a specific CG, which I'll talk about later, but masses were distributed along the top deck and the bottom hull, and the side plates were massless, as well as the stern and bow plates. So the resultant properties, the displacement, which is the displaced volume, times the fluid density, is just easy to calculate. It's just the volume of a rectangular box. What was 1,025 tons. CG was specified to be 0.5 meters, and that's what drove the mass distribution between the top deck and the bottom hull. The CB, there's nothing you can do about that. That's just, that comes out from the geometry there. And it was 0.5 meters below the still water line. So that means that the weight, from a rigid body perspective, the weight was acting a meter above the center of buoyancy. So the meshes were refined so that we achieved sufficiently accurate solutions. Remember, this is a benchmark problem. We were tried to avoid any sort of numerical errors that might creep in because we wanted people to be able to trust the results and then be able to compare their results with them. So if we look at the barge structural mesh, it involved 2,880 rectangular shell elements. The shell element in Hydron XR actually is a macro element. It consists of 4 triangles in a cross-diagonal pattern, and so there's this internal 5th node. But this is all happens internal to the program. It's based on Midland plate theory. However, shear deformation, transverse shear deformation, was expected to be relatively small, and so I wouldn't expect that if one used a well-performing Kirchhoff element that there would be any problems. Regular meshes were used. The top deck and bottom hull each had 10 by 100 elements, so that meant that each element was a 1 meter square. The sides had 4 by 100 elements. So they were 4 elements through the depth, rather. And so these elements were 0.5 meters by 1 meter. Similarly, the bow and stern had 4 by 10 elements, and again, 0.5 meters by 1 meter. This led to an aspect ratio of either 1 or 2. The aspect ratio is defined as the largest dimension of an element to the smallest dimension, that ratio. So it was either 1 or 2. For the barge fluid mesh, we used a 1-to-1 mapping with the structural members. So that left us with 1,440 rectangular wet panels, again with an aspect ratio of either 1 or 2. Panels can be put above the still water line for visualization purposes, but the program ignores them. The fluid panel requires the displacement or velocity really at the panel center, and that because of this 1-to-1 mapping, that panel center corresponded to that center 5th node, and so there was no interpolation required. We could just use the displacements of that 5th node for each element as the displacement for the fluid panel. The panel nominal size was 1 meter, and so we need to look and see how that corresponds to wavelengths. So the most accurate results for this mesh will be for wavelengths greater than 20 meters. Now, why do I say that? If you think of a sinusoid, what we're doing is one can visualize us representing that sinusoid, one cycle of that sinusoid, with 20 line elements. And so clearly we're going to get a very good representation of that sinusoid. Now that's a very fine representation, actually. In practice, one doesn't need quite that fine of a resolution. But again, this was a benchmark problem, and we wanted to make sure that we didn't have any numerical errors, or we wanted to minimize the numerical errors. And so we were saying that at 20 meters wavelength, then we should get very, very good results. Now, if we look at the relationship between wavelength and period for deep water, then that corresponds to, the 20 meters corresponds to about a 3.6 second wave. And as you'll recall, there's very little wave energy at periods below, say, 5 seconds, and so one wouldn't expect the periods, this issue of 20 meters to be a big issue. So The normal modes that were used included the 6 rigid body modes. Remember, these are no deformational modes. Rigid body, by definition, rigid body modes have no deformation. So that means that there are no forces or stresses involved in those modes. The first deformational mode, mode 7, involved vertical bending. So that's shown here in this diagram. The gray is the initial configuration of the barge, and the yellow is the deformed configuration. And so we see that it's bending like a beam in the vertical plane. So that frequency for that, or the period for that normal mode, was 2.25 seconds. Similarly, mode 8 also involved vertical bending, so it was the second vertical bending mode, and it had a period of 0.86 seconds. Mode 9 involved horizontal bending, so instead of bending in the vertical plane, we now had bending in the horizontal plane, and that was 0.66 seconds. This video shows the response of the barge in 8-second head seas, and if we look carefully, we can see that the response of the barge involves flexible motion. This video shows the response in 7-second quartering seas. And again, if we look, we can tell that there's not only vertical bending of this thing, there's also a sort of twisting, torsional kind of response. Mesh convergence is an important issue to consider when developing meshes. So one basic check on our meshes is we need to make sure that our structural mesh is going to give us the total mass correctly. So in other words, from the structural mesh, if we take our structural mesh and calculate the 6x6 rigid body mass matrix, we should get a very good representation for those values of total mass and mass moments of inertia. Similarly, for the fluid mesh, we should make sure that we get the total displacement correct. For the structural mesh, evaluating the natural frequencies is one metric to look at in terms of mesh convergence. In other words, if we were to refine our mesh, do the natural frequencies or normal modes change? The normal modes are important to inspect to make sure that there aren't anything that's obviously wrong, errors that creep in that might be revealed through a visual inspection of the modes. Local modes that should be resuppressed and so forth. So that's an important step to make in terms of when checking our meshes, our structural mesh. For the fluid mesh, again, as we indicated before, it's important to consider how many panels we're going to use per wavelength, and a numerical study is usually required. One possible starting point is to make sure that we've converged in terms of just the simple rigid body motions. The second example in that paper was a wiggly hull, and this example was actually very similar to the barge. The primary difference was that the hull was now curved rather than just flat surfaces. So we again used a one-to-one mapping. However, because of the curved surfaces, we needed to use bilinear interpolation of the nodal displacements, the 4 nodal displacements, to get the displacements at the panel centers. Another benchmark that was been published in the literature is the so-called ISSC VLFS benchmark. VLFS stands for Very Large Floating Structure, and it's an acronym that's become very widely adopted. ISSC is the International Ship and Offshore Structures Congress, and so this benchmark is very similar to the OMAE barge, except it's much larger. It has internal bulkheads as compared to using kind of smearing the stiffness from the internal stiffeners in the plate stiffness. It's longer and wider. It's 500 meters long, 100 meters wide. It's the same depth, 2 meters, with 1 meter draft, but this is in 20 meters of water depth. Now the results for this case were compared for 3 programs and different models. So HydroeXR, which uses the panel method for the fluid and a finite element shell model for the structure. VODAC, which is a Japanese code that uses a very similar fluid model, but it uses a grillage or beam structural model. And finally, Elgian or linearized Green-Nagdi equations were used for the fluid, and a flat plate model was used for the structure. So this is the mesh that was used in Hydran XR. The top plate's been removed so that we can see the internal bulkheads there that run both transversely and longitudinally, and these were there to prevent local modes and to provide the required stiffness for the top and bottom plates. The Hydran XR model involved 8,000 quadrilateral shells for each of the top deck and the bottom hull, and each shell was 2.5 by 2.5 meters. The sides and bulkheads were modeled by 1 meter by 2.5 meter long shell elements. So the total number of shells was 19,280. And the total number of panels is 8,480, again in a 1-to-1 mapping. This plot shows the maximum vertical displacement along a center line of the top deck. And this is in 10-second head seas. So if we look at the horizontal axis, it goes from minus 250 to plus 250. And so the origin was at the center of the top deck. The vertical axis is the maximum vertical displacement, again for a 10-second wave. So this is the maximum vertical displacement at a range of positions along the center line of the top deck. And this is for a 0 degrees wave angle or head seas. So Hydran, Vodak, and Elgian results are compared here. And we see that there are astonishingly good correlation between these three models, which use quite different fluid and structural models. This shows the RAO of the bow vertical displacement. So now the horizontal axis is the wave period, and the vertical axis is the vertical displacement at the bow with meters per meter units or dimensions. That means that it's the bow vertical displacement per unit amplitude of wave. So we show this for 0 degrees, wave angle of 30 degrees, and a wave angle of 45 degrees. And again, we see that the results are, again, given the different fluid and numerical models, substantially in good agreement. Now we look at the RAO of the longitudinal stress at the center of the deck, of the top deck. So again, the horizontal axis is the wave period. The longitudinal axis is the stress per unit wave amplitude, so the dimensions are megapascals per meter. And we see that we get pretty good agreement between these three models. So stress is more difficult to match than displacements because stress involves the derivative of displacement. So with these markedly different numerical structural models, we would expect some difference in the stresses. And we do get some difference, but really from a practical perspective, these are very good. This is very good correlation. So case 2, remember, involves a wetted panel mesh which is kinematically constrained to the structural elements. So the example here is an OTEC cold water pipe. So if we look off to the figure on the right-hand side there, we see a barge with a pipe suspended from it. So OTEC stands for Ocean Thermal Energy Conversion, and it needs a very long pipe with a large diameter to bring up cold water from the very deep water to the surface to be used in the energy conversion. So the barge in this case was considered to be rigid. So this is just the panel mesh for the barge. And the structural mesh was unnecessary because it's a rigid barge. And so really we only needed a single single node to represent the barge, and that was placed at the CG. And it has the mass properties, the rigid body mass properties, and the hydrostatic stiffness properties. The pipe was 1,000 meters long and 2.85 meters in diameter. So you can see that this is a very long pipe. And the connection of the pipe to the barge it was just hung off from the barge with a moment-free connection. So we need to look at how we're going to model that, and also we need to consider how we're going to model the fluid and structural models for the pipe. So the cold water pipe, again, as I mentioned, is 1,000 meters long and 2.85 meters in diameter. So structurally, we can easily model this as a beam. So that's what we did. The pipe structurally was modeled as a beam that's going down the center of this pipe. That's clearly not adequate for the panel mesh. We need to model the wetted surface of the panel mesh, and so we use what we show here in this blow-up is the panel mesh that shows we have elements around the circumference of the pipe. So how do we couple this beam model down the center with these panel elements around the circumference? Somehow we need to constrain the motion of the panel mesh to the motion of the structural mesh. So now I want to talk a little bit about constraints and constrained nodes. So we consider two nodes, each with 6 displacement degrees of freedom. So each has 3 translations and 3 rotations. So we define one node to be a master node with independent degrees of freedom, and that's u sub m and theta m. And we define the second node to be a constrained node with one or more displacements determined from the master node displacements. So we're going to denote those as UC and theta C. This is a common concept in rigid body hydrodynamics where the master node, for example, is the CG of the body, and we can calculate the response, the displacement of any point given the displacement of the CG. It's also a common concept in structural analysis. It's used a lot in structural analysis, and we actually consider expanded constraint options as compared to just simple rigid body constraints. So let's look at the type of constraints. So what I show here is the master node M with displacements u, m, and theta m, and constrained node C with displacements uc and theta c. And then we have this position vector r going from m to c. So one type of constraint, the easiest type, is that the node C has equal displacements to node M. And so in that case, UC was equal to UM, and theta C is equal to theta M. And so these are 6 constraint equations. A relaxation of that constraint is to impose only equal translations. And so that would say that UC is equal to UM, but theta C doesn't necessarily have to be equal to theta M. And then, of course, we have the rigid body constraint. In the rigid body constraint, UC is going to be constrained by both the translations of node M as well as the rotations, and the well-known equation relating the translations of point C to the translations and rotations of point M is shown here. And obviously for rigid body constraints, then the rotations of point C are going to be the same as the rotations of point M. I'd like to point out that this equation for the rigid body constraint involves linear kinematics. So now let's talk about the connection of the barge and the cold water pipe. So as I mentioned before, that we have a moment-free connection between the barge and the cold water pipe. And this cold water pipe is suspended from the barge. I also mentioned before that we've modeled the barge as a single node at the CG with the rigid body mass matrix and the hydrostatic stiffness matrix of the rigid body applied to that node. The hang-off of the point of the CWP is on the barge, but it's not the CG. It's another point, and so we need to use the rigid body constraint from the CG to determine the displacements of the hang-off point. Now, the hang-off point is at the top of the CWP, but the CWP has a moment-free connection, so there we use only equal translations to couple the top of the cold water pipe to the hang-off point. These constraints have to be specified in the structural model. Now let's look at the pipe itself. As I mentioned, a beam is located at the center of the pipe like a spine. We, however, need a panel mesh to represent the surface, the wetted surface of the pipe, and that's what we show here. So somehow we need to constrain the nodes of the panel mesh to the nodes along the spine. So in this case, at each horizontal section with panel edges, a beam element node exists, and the panel nodes are constrained to that beam master node. So the panel mesh involves 12 panels around the circumference and 700 panels along the length. So HydroNXR allows interface elements to be defined in the structural mesh. This is for convenience. So the interface elements are structural elements, but they really have no properties other than area. They're dummy elements. They're meant to correspond to fluid panels in the fluid mesh. So we use these for the barge, and we also use these for the wetted surface of the cold water pipe. And then HydroNXR from these panels, from these interface elements, can create the panel mesh automatically from the interface elements and from the shell elements. So let's look at some special modeling issues for the cold water pipe. We know we have to define the modes that we're going to use. So for the rigid body modes, we used surge, sway, heave of the whole system, but we couldn't use well the rotational modes for the whole system because the cold water pipe is not rigidly connected moment-wise to the barge. So we only included roll, pitch, and yaw of the barge for the 6 rigid body to define the remaining 6 rigid body modes. However, for the pipe, we did need to restrain the torsion of the pipe. Otherwise, it would just be able to spin without any restraint. And so there was one structural node of the cold water pipe that we restrained in torsion to prevent that rotation. Spine elements must have mass moments of inertia because of the diameter of the pipe. So in other words, this was a large diameter pipe. All of the mass of the pipe was around the circumference there, and so we wanted to include the mass moments of inertia of the pipe. The panel mesh models the external fluid, but what about the internal fluid that's trapped inside the pipe? So what we did there is we added that mass, the mass of this internal fluid, to the pipe mass in the x and y directions. But we decided that we would not add any additional mass in the z direction. So if you think of a vertical pipe that's open at the bottom, clearly if it moves in the x and y direction, it's going to push that mass, that water mass, along with it. However, if it's moving up and down, it's how much mass is going to travel with that pipe is a little different issue. And so we decided not to include any mass in the z direction. Now, the issue of do we include mass moments of inertia for that internal entrained water, and that's a modeling decision that needs to be made, and in this case we decided not to include it. I'd like to make some comments on the structural modeling. The more motion that we allow, the lower the forces, and conversely, the less motion allowed, the higher the forces. So an example of that is the attachment of the cold water pipe. Because we allowed relative rotation between the top of the pipe and the barge, that meant the moment was 0. If we had enforced equal rotations between the barge and the top of the cold water pipe, we would have imposed quite a bit of deformation and moment on the top of the pipe. Simplified structural models have advantages. Normally we want to try to make as simple a structural model as possible that's still sufficient to capture the fundamental behavior. The fundamental behavior we're most interested in global hydroelastic analyses is the global behavior. And in that case, sometimes beam models may be useful, as it was for the pipe. However, if we want local response, for example, detailed stresses in the perimeter of that pipe walls, then maybe that's not going to be a sufficient model, and we would need to use a shell model for something like that. We want to make sure that we keep in mind that we're going to have to couple the structural model with the fluid mesh, and so that's also an issue that drives then how we're going to do how we're going to model both our structure and our fluid. The next example I want to talk about is the semi-submersible mobile offshore base that I talked about in a very early video in this series. This is the J. Ray McDermott example or concept. It involved 5 very large semi-submersibles connected together to form a 1,500 meter long mobile offshore base. The connection of the modules was at the deck level only to reduce the forces. However, because of that, it does allow more pitching of modules. So this sort of a structure admits 2 kinds of models, I would say. The RMFC, so-called RMFC model, rigid module, flexible connector model, which assumes the modules are rigid and they're only connected by flexible connectors. So the only flexibility is in the connectors. So that means that each module is rigid and has 6 degrees of freedom, and so there's 5 modules. So the entire system would have 30 degrees of freedom, just 30 degrees of freedom. A more detailed finite element structural model is going to use far more degrees of freedom than that, far more degrees of freedom than that, and we would need to use a reduced basis for that sort of a model. What's shown here is the panel mesh, and the panel mesh was the same for both models when this thing was analyzed, and the 2 models, results of the 2 models were compared. So the structural models, again, the rigid module, flexible connector, 30 degrees of freedom. The finite element structural model, far more degrees of freedom. We needed to find the natural modes and use a reduced basis. This shows the U.S. Navy MOBE model tests. I also mentioned these in the very early on video in this series. And this shows the model of one module in those wave tank tests. Now the structural framework was essentially a 3D frame. You can't really see it so well here, but if we look at the pontoon, basically there was just a beam inside this outer shell that formed the hydrodynamic framework. So the structural model, we used beam elements, and then we had to couple these meshes. I have to say that coupling the meshes was a lot of work. And this corresponds to my case 3 that I talked about, where the structural mesh and the fluid mesh don't have a clear correspondence. And as I mentioned before, I do try to stay away from these kinds of situations. So this ends this video, and really it ends this video series. The next videos are going to be working through the OMAE barge example, very detailed work through, showing step by step how to analyze that OMAE barge using HydroNXR.